Start.
Not bad. वापस लैपटॉप नहीं लैपटॉप है फुटबॉल
टेनिस बाकी टेनिस
एक ही फायदा फोल्डर है कौन सी क्लास कब से पहले कोई नहीं लेट पहली क्लास फर्स्ट क्लास फर्स्ट क्लास चाहे 1 बजे वो लेट आएंगे लेक्चर नंबर 6 का सारा Okay, let's get started with the class. Today we shall be covering these three things, an analysis of course, and the results. We shall see how we can display the results and how we can understand the results. Okay, and I told you that for understanding the results it is necessary that you know the local axis system. Yes, without understanding local axis system, you cannot interpret the results because all the results are expressed in terms of local axis, which are 1, 2 and 3. Then we shall also cover design. ETABS can design line elements, beams and columns, as well as walls, shear walls. So we shall be looking into beams and columns, the design of beams and columns. And in the end we shall talk about report generation, because one of the deliverables is, I mean, in addition to the shop drawings or construction drawings, you may have to submit a design report. So the major part of the design report comes from the software. So we shall see how we can have a presentable design report. Okay, so let's begin with the analysis. The structure has been analyzed, and we'll go to display menu to see different types of results. For example, the first one is here, show deformed shape. Using this option, you can see the deformed shape of the structure under different load patterns or load cases, I should say. Deformed shape is actually the elastic curve. You remember from mechanics of material, you used to draw the elastic curve or the deflected shape. It's the same thing. So when you click this option, the software asks you that for which load you want to check the deformed shape. Either you want to see it for floor finishes, roof, live load or partition load or live load. This decon 1 and decon 2, these are combinations. Decon 1 is default combination, which is 1.4 times dead load, and decon 2 is 1.2 dead load plus 1.6 live load. Actually, these are same combinations as are provided by ACI code. ETABS has its own name. It calls these combinations decon 1, decon 2, decon 3, decon 4, because we have not introduced the earthquake loading and wind loading. That's why we only have two combinations, decon 1 and decon 2. Okay. Otherwise, I mean, if you have earthquake loading and wind loading, these load combination will be more than 10. By the way, in our next class on Friday, which is tomorrow, we shall learn about earthquake loading, wind loading, and how we can import the grids from AutoCAD. So, do we have AutoCAD in this laptop? No. So next time when you come, have AutoCAD, and if you can have an architectural plan, it's better. Otherwise, I'll see if we can bring. Or I just want to draw the grids on AutoCAD and then import it in ETABS. Okay, and these combinations D wall 1, D wall 2, these are related to the design of shear walls. Okay, right now we don't have a shear wall here, but we can have one. Maybe on Friday I can also cover shear walls. Remind me. Okay. So let's see the deformed shape due to live load. Press OK. So this is deformed shape due to live load. If you let me go to the plan. Okay, if you right click on any joint, for example like this, then you will see the displacements at that joint, and there will be 6 displacements, which are 3 translations. 3 translations means delta x. What happened? Okay, so right click on the joint and you will see 3 translations, delta x, delta y and delta z. These are 3 translations, and you also see 3 rotations, theta x, theta y and theta z. Means rotation about x-axis, about y-axis and about z-axis, right? That you see. And because right now we are looking at deformed shape due to live load, which is in the direction of gravity, that's why delta x and delta y will not be significant. Delta z will be significant because it's in the direction of gravity, and delta z will be negative because z is vertically up, delta z is downward, so you see a negative sign. Okay.
So why but negative?
Sorry?
So negative is
Z is upward and deflection is downward. Deflection is downward, that's why you will have a negative sign with delta z, or translation in z direction. Go click on the support. Right click on the support. Right click on the fixed support at the bottom. What do you see?
0, 0.
Moment. What do you see? What 0? Which translation and rotation are 0? All of them. Why all of them are 0? Because it is a fixed support. Fixed support does not allow any translation or any rotation. That's why all the 6 values are 0. Okay? Okay. If you have a hinge support, do you have a hinge support somewhere?
Yes, sir.
Okay. If you have a hinge support, although we changed all the supports to fixed, but I think we deleted one column and then inserted it again. So when you do that, you have a hinge support. So if you have by any chance a hinge support, click on the hinge support now. When you click on the hinge support, you will see that all the 3 translations are 0 and all the 3 rotations are non-zero, right? Why they are non-zero? Because hinge cannot resist rotation, it allows rotation. That's why it has rotation. Okay? So hinge has 3 degrees of freedom, which are translation. Fixed support has 0 degree, and any other joint has 6 degrees of freedom, right? Any other joint, any other beam column joint you have, it has 6 degrees of freedom, and you have all 6 values. Right? I'm not sure about this notation. You have to find out rotations. Some of them may be positive and some of them may be negative. I forgot that ETABS considered clockwise positive or clockwise negative. So you can make a question mark to later find out what is the notation used in ETABS. Okay, you can go to the help and see the notation. That's no big deal. Okay. So you can look at the deformed shape under any load you want. Right now we don't have earthquake load, otherwise when there is an earthquake load you will clearly see a lateral deformation. Okay. Right now you have mostly deformation in the direction of gravity. You have it back? Okay. Now let's again go to the display menu. So you see the deformed shape. Right on the top you have this button which says show undeformed shape. So if you want to just go back to normal, click on this and you will have undeformed shape back. And you have buttons here in the toolbar as well. Show undeformed shape right here and show deformed shape. Then let's try to see forces, member forces. Show member forces / stress diagrams. Okay. The first thing you would like to see are support reactions or spring reactions. We don't have spring in here. In some cases we may have spring when you have something compressible, but right now we have our regular support. So when you click on this, It will ask you for what load case you want to see the reaction, or for what combination. For example, I say decon 2, and let me write it for your reference. Decon 2 is 1.2 dead plus 1.6 live. That's the name given by ETABS. It's not a standard name. So for decon 2, but this is the most popular combination. So you see reactions. When you click this, on all the supports you see values. Let me go to the elevation number 1 and see what are the reactions. Okay, this support, this one, in my model this was a hinge support and all others were fixed support. So on the hinge support you see two reactions, okay, horizontal and vertical. There is no rotation, there is no movement, because hinge support allows rotation. When you allow something, then you can't resist that thing. So allows rotation, no reaction in terms of movement. But right here you have 1, 2 and 3. Similarly is here 3, 3 and on the last one. Right click on any of the supports and you will see the values. This is a hinge support, that's why you only see reactions in terms of forces, right? Not in terms of movements. All the three movements are 0, right? That makes sense? Now look at the magnitudes of the reactions. Which is the highest magnitude? Again, we did talk about the local axis system of joints. Joints also have a local axis system, but you can guess from here, looking at the magnitude, which axis out of 1, 2 and 3 is vertical. Look, we are looking at the reaction for decon 2, which is 1.2 dead and 1.6 live. Both live and dead are gravity loads. So, if you have gravity loads, then what do you expect? Which reaction should be higher in magnitude? The horizontal reaction or vertical reaction? Vertical reaction, right? So, vertical reaction should be force 3. Along axis 1 it is 2.5, axis 2 it is 1.5, and along axis 3 it is 39.6. That tells you that axis 3 is actually vertical axis, okay, because it has maximum reaction. We are supposed to have maximum reaction in vertical direction because we are looking at the gravity load combination, okay. So at least you understand from here that the local axis system, in local axis system for the joints, 3 is up. Write a note on your copy about the local axis system of joints. Just write local axis system of joints and in the bracket you can write leave it from the alpha. Read the local axis system of joints from the alpha. It's actually simple, you just need to go and check what are the directions. But from the face of it, you can see 1 and 2 are horizontal, 1 and 2 are in the plan, and 3 is vertically up, right? Yes, you're okay. You can check for magnitude for load, for plastic load, like and if you want, but in real life, structure is designed for combination. If all cases, check for line. Okay, so the reaction here, the vertical reaction is 39 and my units are kips. This is 39 kips or 39,000 pounds, right? And all the three movements are 0. Now let's check the reaction for the other one. Click on the other one. Let's click on this one. Okay. Again you see that the vertical reaction, which is along axis 3, is 66 kip, 66,000 pounds, right? So huge reaction. And look at the movements. You can see that one of the movements is much greater than the other two. Let me change the units to kip fit. Right now I have kip inch. Kip fit. Okay, that's better. Generally we use these units in real life, kip and fit. Okay. My force or reaction in the plan, axis 1 and axis 2 is very small, but along axis 3 it is significant. Okay. Right now it appears to me that it's like this. If this is 3, vertical is 3, then can you guess which one would be 1 and which one would be 2? This one would be 1 or 2? Based on these directions, I mean, if I switch it like this, then it's a different story. But it may be like that as well, but I'm just assuming that it is like this. So which one is this?
1, 2.
Use the right hand rule.
The 2.
If I keep this as 1,
The 2 will be
2 right hand rule is 1 to 2, 2 to 3, and 3 to 1.
Yes.
Okay?
ये 2
3 to
होगा कह रहे हैं
1. This other way? No. So if I keep this as 3 and this as 1,
yes sir
then
सही हो जाएगा this will do
actually this one is like this.
yes
It's out of the plane.
yes sir
Okay. So 3 to 1 is 2. So it means this is 1 and this is 2. It's 1 to 2, 2 to 3, and 3 to 1. So 2 to 3 and 1 is out of the plane. 1 is out of the plane axis. So 3 is vertically up. Now look at this. Look at the movements. Try to understand the movements. One thing is that the support where I have clicked is what type of column? Is it a head column? It's an edge column. Okay. What do you expect in terms of movement from an edge column? It's a column like this, right here. Look at that column. Okay? Or look at that column. That column right under the view. For that column, on the right side and on the left side, you have similar situation. So the right side load and left side load, they balance each other, and you won't see significant movement about which axis?
one axis one
Like this.
about axis 2
Which axis we are talking about? We are talking about this axis.
yes sir
This axis. This movement is about this axis. Right? No matter it's 1 or 2, I'm just trying to explain which axis. I mean, I'm trying to explain you that there will be one movement and the other movement will be insignificant. So movement about this axis is insignificant. But the moment about this axis, look, that axis, you have on the left side of the column this all billing, but on the right side, there is nothing. So, the force is only on one side and the resultant would be somewhere here, and that is eccentricity. So, you have this movement, and that is about that axis. Okay? What about the third axis, which is vertical, passing through the centroid? That movement, that axis actually, if any movement exists, that is twisting movement. But because we don't have any lateral load or any point movement, we don't have twisting movement. Which axis is up? Three. What is the movement about 3x? 0.029. That is actually torsion. So we are quite sure that torsion would be absent. Okay? If I am not wrong in terms of axis. The only movement you have is M11 or M1. Okay? So because the fact that this is an X column, you only have M1. If this is a corner column, then you will have M1 as well as M2, and that column will be called as biaxial. It will be a biaxial column. Movement about both the axes, right? So you see that it's not just about the software. You have to understand the basics of structural analysis. Okay, now let's check a corner column and try to verify what we are saying is correct. This is a corner column. Okay, look at this. First of all, look at the reactions, force. Again, you see that 1 and 2 are very small and 3 is significantly large. So, you have a vertical reaction. Okay, how about the movement about axis number 3? It's 0.028. This is vertical axis 3, and movement about axis 3 is twisting. We don't have twisting, but you have M1 and M2. 1 and 2 are axes in plane. Okay? The fact that this is a corner column, it should have biaxial bending. It should have movement about both the axes. Okay? That's why you see movement M1 as well as M2. So you see that only a person who has good understanding of these basics of structural analysis can understand this thing, and he can pick the errors. He can find out the errors. If you don't have biaxial bending at the corner column, then there is something wrong, right? So you have to have basics of these things. I mean, you should have clear concept on this. But this is only happening because it is a fixed support. If you have a hinge support here, then you won't have movement at the support even if it is a corner column. Okay? Yes. Yes, we are talking about local axis. Yes. No, right now we are talking about support. This is at the foundation. Okay? These are joint axes. Okay? So we have local axis for the joints separately, for the line elements different, and for the area elements different. Okay? So right now, gentlemen mentioned that for the column we said that the longitudinal axis is always 1. That's what I said. For line element, no matter it's a beam or it's a column, local axis is 1. That's right. But right now, we are talking about the joint, the support. We are looking at the reactions. So that's why it's different. Okay, now let me go back to this corner column which has a hinge support. You see, all the movements are 0. No matter it's a corner column, you have 0 movement. Now let's pick, yes? Sorry? No, you have only 3. This 1 and 2 is insignificant.
Insignificant तो है लेकिन 1 एक्सिस से लॉन्ग ही आ रहा है तो आपने 2 एक्सिस का वर्क 2 का दिया नंबर.
What did I say about 2? Where?
ये जो आपने बताया ट्राइडेंट रूल लॉन्ग होरिजेंटल सर आपने 2 लिखा हुआ यहाँ
1 and 2 both are horizontal. 1 and 2 are right here on the ground. 1 and 2, or it may be 1 and 2, but both of them are in plan, and 3 is vertical. Look at the corner there. You have 3 axes, 1, 2 and 3. Is 1 horizontal? How about 2? That's what I'm saying. 1 and 2 both are horizontal axes. Although they are orthogonal to each other at 90-degree angle, but both of them are horizontal, in horizontal plane. 3 is vertically up. Okay? Okay, now I want to pick a central column. For example, let's pick this one. What is the designation of this column right now as per our grid lines? This is 3 and C. So I go to elevation number 3 and right here 3C. This is a central column. What do you expect in terms of movement for a central column? It may not be perfectly 0, but it will be very small value. Look at the force, same pattern. You have reaction in direction 3, and look at the movements 1.3, 0.39, 0.028. So all the 3 movements are insignificant because the column is centrally located, okay, and the load is balanced from all the 4 sides equally, right? This type of column I think you have designed. Have you designed or maybe this type of foundation you have designed, the foundation which has only axial load, right? You have not designed an edge foundation for the edge column or foundation for the corner column. Okay. Sorry? Okay. Now there may be a possibility that you have moment at the central column as well, right? When you may have some unsymmetrical dimension. For example, this is 15 feet and here it is 20 feet. So there is an unsymmetrical loading, unsymmetrical dimension, or the dimension is same, but on this side you have a different load, say 50 pounds per square foot, and on this side you have like 100 pounds per square foot. So the magnitudes of resultants are different. That's why even the dimensions are same, still you have value of movement. Okay. So yes. Yes.
So if we have movement in that case too.
Yes, that creates an unsymmetrical situation. That when you have an opening on one side, it means that the load from one side has reduced, and on the other side it is more. Okay. So you have an unbalanced movement, right? Let me quickly sketch it for you. Okay. This is the plan of a typical space frame. The corner column, for the corner column, the trajectory area is this much. This is the trajectory area for the corner column. It is rectangular, right? Where is the location of the resultant? You draw the diagonals. Wherever diagonals intersect, that is the location of the resultant. Right? You draw the diagonals, and right here is the location where the resultant is acting. How can you find that resultant? Look, the load on the slab, say it is 50 pounds per square foot. That's the intensity. You multiply that 50 pounds per square foot with this trajectory area, which is in feet square. So, intensity of the load into area, what you get? You get the load. So, for this column, this is eccentricity, I call it EX, and this is eccentricity EY. I call it EY. So if the load here is P, the load acting is P, then this load is producing two types of movement. P into EX and P into EY, right? So I call maybe M1 P into EX and M2 P into EY. So that's what biaxial bending is. Okay, that a column or a support, its support has two movements. As opposed to this, if you pick any edge column, half from this side and half from this side and half from this side. See? So the trajectory area is again rectangular like this for an edge column, and when you cross and find out the location of the centroid, that will be somewhere here, right? The P is acting here. So this column only has what? EY. There is no EX because it's exactly on the line of the column. So it has only one movement. M1 is 0 and M2 is P into EY. So this is a case of a uniaxial column. Most of the edge columns are uniaxial, but it's not a universal truth. Again, those things will affect symmetry of dimensions and symmetry of loading that can convert an edge column into a biaxial column, right? And how about the central column? Central column has a trajectory area like this, and its centroid lies right on the column. So for this one, M1 and M2 are 0. This is true when you have symmetrical dimensions and symmetrical loading. Okay? If you have unsymmetrical loading, unsymmetrical dimension, then you may see variation. So you don't have to believe on the results of the software blindly. You have to look at the results and see whether they make sense or not. If they make sense, that's fine. If they don't make sense, then you have to find out the problem, that what is the problem, and solve the problem. Okay? Everybody's clear about this? Very nice. So after reactions, I shall go to other forces. Forces are shear force or bending moment. Okay. Again, softwares ask you for what load case or what load combination you want to check the results. Econ 2. Let me check decon 2. And what do you want to see? You want to see axial force, shear 2-2, shear 3-3. Forget about inclined shear. You want to see torsion. You want to see moment 2 or 3. Based on our local axis system, generally for the beams, shear 2 is significant. Okay, shear 2-2 for the beams, shear 2-2 is significant, especially for gravity loading. Okay, and moment 3-3 for the beams. Okay, and if you have gravity loading. But if you have lateral loading, then you can check shear 2-2 as well as shear 3-3, but I think shear 2-2 still be significant. This is, I'm talking about beams. So in general, for beams you will see shear 2-2 and moment 3-3 or simply M3. So if you look at shear 2, you see something like this, but we go to an elevation. Okay. Okay. You see that it is providing shear at a distance at the edge. That's actually the dimension of the column. Okay, that's the dimension of the column, and maybe it also takes care of the critical section. You know, critical section for shear is from the face of support. It is at a distance
D by
2.
Yes, sir. For two-way shear, D by 2.
For one-way shear, it is D. So we are talking about one-way shear here.
Sir.
So I think it actually gives you shear force at a distance D from the face of support. But we may have to reconfirm. If you right click on this beam, you will see this panel. And on this panel, you have several things. Number one is the equivalent load. What do you mean by equivalent load? Equivalent load means the load which software has transferred from the slab to the beam based on the tributary area. And you see these point loads and movements at several locations. These are actually points where slab is connected to the beam. Okay, in real life slab is continuously connected to the beam, but in our case slab is connected to the beams only at the points where we have mesh, right? So that's why you have at every meshing point you have these point loads. Okay, look at this. This one is shear force diagram. This one is bending moment diagram. This bending moment diagram looks opposite to what you generally draw.
Yes.
It's mirror image of that. This is positive bending moment, and at the support it is negative bending moment. You actually draw it, you know, flip. So, and this at the bottom is the deflection. All this is for decon 2 combination, but you can pick the desired load or combination from here. For example, for live load it's different. Let me see for decon 2, and you can see the respective values at the edge here. For example, shear here is 23.38 kip and moment here is 71.8 kip. This is right now the radio button picked up is show maximum, but you can pick this, scroll the value, When you scroll the value, you can actually scroll it anywhere. When you scroll it, you will see that these values will change. For example, right at the center somewhere, the shear value will be approximately 0 or minimum. You see that? 0.94, or if I be little fine, then we may catch 0. But at the center, shear is approximately 0 or minimum, and moment is maximum, which is around 32 kPa, right? And at the support, you have a negative moment like this, -71 is the negative bending. And look at the deflection. The deflection right here is maximum, and deflection is small, that's why I choose in inch. In inches it is 0.044 inch, but generally the deflection is checked for live load. So I picked live load for deflection, and for live load it is 0.006. The way we design it is that we don't want deflection for dead loads. That's why when the beam is constructed, we prefer to have a camber in the beam. Okay, so the dead loads neutralize the camber, and the live loads have positive deflection, I mean downward deflection. So the reflection is generally checked for live load. Or in other words, we say that it is preferable that the structure should not have deflection for dead loads, okay, especially for self-weight. But you can check the maximum deflection, show maximum. The maximum deflection is 0.006, which is at 90 inches. 90 inches means around 7.5 feet, right, from the starting point. ETABS name the two edges of the beam as end I and end J. Every longitudinal member has one edge is I and the other end is J. Okay, that's an additional information. You can see here I end and J end. Okay. Okay, now look at the column. Right now we were looking at shear force diagram for the beams. Yes, let me quickly also see the bending moment diagram for beam M33. This is a bending moment diagram, and I said that this is flip. It's a mirror image. At this point you can change it. If you go to options and you say uncheck this one, movement diagram on tension side. Right now it is checked. If you uncheck this one, you will have the diagram which you generally have been plotting, right? In the middle you have positive bending moment, in pale color or yellow color, and at the edge you have negative bending moment, which is in red color. From the options, show movement diagram on tension side. Uncheck this option. Okay. And look at the bending moment diagram closely. You will see that an interior support, you have significant negative movement.
Yes, sir.
But at the edge support,
Yes, sir.
you don't have significant negative bending moment. Okay. So, which is generally true. Do you remember the coefficients?
Yes, sir.
Do you remember the coefficient for the design of continuous bending moment, continuous beams?
Yes, sir.
The edge coefficient, the negative bending moment, is smaller. If it is a hinge support, then it is 0. Practically maybe something. But at the interior support, you have significant bending moment. So at the discontinuous edge, you see that negative bending moment is very small. But at the continuous edges, which are interior edges, you have significant bending moment, right? Yes. Leftmost column, this is bending moment diagram. Now this bending moment diagram is first degree diagram,
Yes.
and the diagram for the beams is second degree. Why? Because on the beams you have, this may be third degree as well, you have distributed loading, not UDL, it's a distributed loading. From the slab, the load which is transferred is distributed, but in case of column, there is no distributed load. The movement is coming from the beam, right? And then there is no load on the column. That's why you see linear diagram. If you click on the column, you see a linear diagram. What do you see? At the top edge, the movement is 35.07 kip feet. At the bottom, because you have a hinge support, what should be the moment? It should be 0. And you can see that right here, at the bottom, the moment is 0. Okay? And in between you can see movement anywhere. So this is the movement for which you shall design the column. Maximum movement. Sorry? The other columns, right click on them, and you have this thing. The movement on these columns is small. Which movement? This is M33. Okay, movement is small, but let me. Minus is negative bending moment. I mean, it's just. Let me see. M22. Okay, now you see that this is an edge column, and for this edge column, M33 was small, okay, and M22 is significant. So it only has one movement. Now that's different from those axes. Those axes are for the joints. Now I'm talking about axis for the column. Okay. So you have significant movement at the top, 56.91, and at the bottom you have negative bending moment, which is 33.13. Actually, this 33.13 is right here at the support. If you click on the joint and see the bending moment, it will be same as 33.13. Now I have just briefly showed you these things. You have to work on this, and you will have questions maybe, but if you have this basic understanding and structural analysis, then you can easily understand the results. Let me see if I want to show you. So using this option, you can see for any load case, any load combination, the forces you want. For example, axial force, you will see that in the beams you won't have significant axial force, but in the columns you will have significant axial force. Okay, if you click on the beam, the axial force will be very, very small. You see that it is 1.62 kip at the edge, but in case of beam or in case of column, the axial force is, look, 62.86 kip, and at the bottom it is 66 kip. So 62 at the top and 66 at the bottom. Okay. With the scale factor, you can make it look bigger and smaller. Okay. Try it. Okay. At the top you have 62 kips, at the bottom you have 66, because at the top the self weight is not included, at the bottom the self weight is also included. Okay, so that's how you see. And you can also notice that the axial force in the central columns is higher as compared to corner column. This is actually an edge column basically, but at the column, at the corner, the axial force is smaller. Okay, tell me, in this structure, which column would have highest axial force? A corner, edge or center? Center. Central column have minimum bending moment and maximum axial force, right? And that you can see. For example, I go back to column 3C, which is actually a central column, and look at the axial force. It's 89 kips versus 66 kip for the edge column. Okay, everybody is clear about this result thing? Okay.
Inside this frame negative flow करता है ना? Sir, inside the frame negative चीजें flow करता है.
We have a 2 minutes break in the class.
Sir, inside the frame negative flow करता है, positive flow करता है.
Yeah.
कोई भी मतलब कि आपका बेंडिंग मूवमेंट आएगी तो वो इनसाइड द फ्रेम अगर आएगी तो बी है ना, बी पे बीम की अगर हम बनाएंगे बेंडिंग,
ये आपको इसकी डिफॉर्म शेप से देखना पड़ेगा, मुझे श्योर नहीं है. ये मैनुअली आप करते हैं तो वो डिपेंड करता है आप क्या करते हैं. आप लेफ्ट से देख रहे हैं, राइट से देख रहे हैं या अंदर खड़े हुए देख रहे हैं, वो आपको इसकी डिफॉर्म शेप से क्रैक करना पड़ेगा कि ये क्या वो ले रहा है. लेकिन डिज़ाइन में इसकी इम्पोर्टेंस नहीं है. अगर सपोर्ट पे नेगेटिव बेंडिंग मोमेंट आ रहा है कॉलम में, तो आप ये नहीं करेंगे कि आप एक साइड पे स्टील देंगे और दूसरी तरफ नहीं देंगे. कॉलम्स में स्टील आप पूरा चारों तरफ डिस्ट्रीब्यूट करते हैं, तो नो मैटर कॉलम ऐसे बेंड हो रहा है या ऐसे बेंड हो रहा है, स्टील वैसे ही आएगा. तो आपने वो नेगेटिव मोमेंट की वैल्यू लेनी है और उसको डिज़ाइन कर देना है. ठीक है, जो स्टील आएगा उसको चारों तरफ प्रोवाइड कर देना है.
तो मैक्सिमम मूवमेंट आएगा नेगेटिव और पॉजिटिव
नहीं, जरूरी नहीं है. हाँ, कॉलम के केस में ठीक है, कॉलम के केस में ठीक है, बीम के केस में डिफरेंट है. बीम में बेड पे पॉजिटिव के लिए डिजाइन करेंगे, सपोर्ट पे नेगेटिव. कॉलम में आप देखेंगे
तो मैक्सिमम
जो आ रहा है उसके लिए करते हैं. वो सॉफ्टवेयर की मर्जी है. आपने खुद पढ़ना है जाके कि कौन सा आई है कौन सा जे है. ये देखिए, अभी ये रेड स्पॉट है, देख रहे हैं रेड स्पॉट. ये कहाँ पे है? यहाँ पे है. ये एंड जे है. ठीक है, दिस इज एंड जे एंड दिस इज एंड आई. तो ये कोई ऐसी चीज नहीं है जो आप मेमोराइज कर सकें. ये आपको कौन सा स्पॉट ही देखेंगे कौन सा आई है कौन सा जे है.
अली को आगे तो अली को आगे भाई आज रीडिंग लेनी है, आज कोड भी लेनी है उसकी. ओवन ड्राइव ले ली ये हो गया. What's the next going? Grade cut होगा तो geometry cut होगा automatically अरे फुटबॉल का डिजाइन का बोला वाला
Now we shall move to the design menu. When you click on the design menu, you see several options. For example, steel frame design. You can use this for designing steel structures like the one you designed in your steel structure third year. You can design a truss. You can design a frame structure, steel columns, steel beams. Okay. Right now we are not going into that. You can see the second option, which is concrete frame design. Concrete frame design. The third option is composite beam design. What is composite? Composite is the beam is made up of steel and slab is made of concrete, and they are connected through shear connectors. Okay. Steel joist design and shear wall design. Our scope of this class is concrete frame design and shear wall design. These two things we shall be designing. So when you go to concrete frame design, the first option you see here is select design combo. Select design combo means the combinations provided by ACI code, those design combinations you can pick from the library and ask the software to design your structure for those combinations. Okay, so these are not the combinations of the software, these are combinations of ACI code. When you select on these, you see list of combinations. Okay, right here it says choose combination. This is list of combination and these are design combinations. I mean, this is complete list, and from here you can select and add into your design combination. ETAB will design for those combinations which are here in the list. If you select them, all of them, and remove them, now right now there is no design combination for which ETAB will be designing. Okay, so what you can do is you can pick this one and this one. We don't have a wall right now, so I'm just picking the gravity combination for the frame. Add it, and you can also see the combination. Click on any one of them and say show, and you will see it is what? All three are dead loads: floor finishes, partition and roof, and the scale factor is 1.4. It is actually the first combination in the ACI code, which is 1.4 times dead load. It's not, in true spirits, it's not a combination, it is just a factored load. I mean, this represents a condition when the building is empty, right? There is no live load in the building, it's only dead load. You know, for example, in the evening when the campus, when the department is empty, you have mostly dead load. Although this furniture is live load, but you can, similar to that situation when the building is empty, or when the building has been constructed but it is not occupied, it only has dead load. Decon 2, show. You will see that for dead load it's 1.2, for live load 1.6, and these are also dead loads, partition and roof, factor is 1.2. So it's actually 1.2 dead load and 1.6 live load. You will see decon 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 when you will have earthquake and wind loading. Okay. So right now we will stick only to these two load combinations which are already included. Then on the very next click it says start design / check of structure. Design means software will provide you the reinforcement. Okay. Check means you have provided the reinforcement by yourself, and ETABS will check whether that reinforcement is sufficient or not, and that option is used for already existing structures for which you have to check the structural integrity or sufficiency for the loading. But when you are designing a new structure, it's actually design, start design. It's about design actually. When you click on this, it just runs the design and you see this thing. Let me change the units to inches, hip inch. Okay. Now let me show you a typical design on elevation 1. The first thing you need to learn is, if the member is red in color, it's not very clear, but these three are green, the beams are green, and this one is red. Red means the beam has failed. Okay, failed means it is insufficient. You need to increase the size of the beam. Red means a failure. Okay, or failure in other words means that the dimensions of the beam are not sufficient to take care of the load. You have to increase the dimensions. Okay. What do you see right now? The numbers here on the beam are longitudinal reinforcement. See on the title bar what it says. It says longitudinal reinforcement, right?
Yes.
Do you read longitudinal reinforcement? Yes. Do you see longitudinal reinforcements written somewhere on the screen? Do you see a screen? There you go. You can't see the screen. On the title bar, do you have a laptop somewhere? Show him where you can see longitudinal reinforcement. Yes, on the title bar it says longitudinal reinforcement. Okay, what does longitudinal reinforcement take care of? What force? Which force? Bending moment. Longitudinal reinforcement takes care of bending moment. Okay? And shear stirrups are for shear, or stirrups I should say, are for shear. So when you finish the design, or when software finishes the design, the first thing it shows you is longitudinal reinforcement. Okay? Now you need to understand what this longitudinal reinforcement is and how you can actually use the values to finally provide the steel. Okay. Yes, what's your name? Adib. Okay, Adib. Tell me the longitudinal reinforcement for any of the beam. There are 6 values, 3 at the bottom and 3 at the top. Okay, who has? You have? Okay. Yeah. Okay. For any one beam, show me what's the value here. And make sure the units are in inch. Keep inch or pound inch, whatever, in inch. Right? Okay. For any one beam, tell me these values.
0.221.
0.
At the top.
Oh, at the top. 0.221. Okay. This one?
It's the same value.
0.221. 0.6 double H 2.
0.5.
This one?
Yes.
0.5 8 35.
0.6500.
0.65 00.
0.4488.
0.4488. Is it an edge beam?
Yes.
Okay. It's an edge beam. That's why you don't see much of negative reinforcement. It's an edge beam. Okay. Edge beams mean it has no other beam on this side. Okay. Give me a value, these values for an interior beam. Not the first interior beam, the second beam. The first is fine as well. Look at elevation, any elevation, and give me these values for an interior beam. You know, on elevation number 1, although elevation number 1 is at the edge, but that's for column. The beams are interior beams, you know, edge beam and interior beams. So give me the value for an interior beam.
0.4432.
0.4432.
0.1638.
0.1638. 0.5. 111. Yes.
0.32.
0.32.
04.
04.
0.3975.
0.3975.
0.7317.
0.3317. Okay. Interior beam is better to understand at first time. The reinforcement written above the beam is top reinforcement. And reinforcement written below the beam is bottom reinforcement. Okay, the first thing. Yes, this is actually, yes, that's what I was going to tell you. These numbers are actually areas of steel in inch square. These are AS in inch square. Okay, these values are areas of longitudinal steel in inch square, right? Now, for an interior beam, you will see that you have negative bending moment at the edges and positive bending moment at the center. Okay. For negative bending moment, you provide steel at the top, and for positive bending moment, you provide steel at the bottom. Okay. At the middle of the section, you have positive bending moment. That's why you will see that the bottom reinforcement is significant. Okay. And at the edges, you have negative bending moment. That's why the top reinforcement will be higher.
Yes, sir.
So actually the three circle values are our main reinforcement. Okay. The one at the center, 0.397 is bottom reinforcement, and the two at the edges on the top are top reinforcement. Okay. Now, I won't go into detailing because that's part of your PRC course. I will just tell you how you can calculate the steel bars. Okay. To calculate the steel bars, number of steel bars, you need to know the area of one bar. Okay. Now, this designation, maybe I'm not sure if you remember the designations. The FPS, in FPS system or US customary system, designations are bar number 3, 4, 5, 6, 7, 8.
Yes.
Okay. And I told you that generally in beams, we use number 4, number 6, and number 8.
Yes.
Okay. For example, let's say we use number 4. Okay. Area of one number 4 bar. Anybody remember that? It's 0.196 inch square. Okay. 0.196 inch square, or some people simply use it 0.2 inch square. Okay. And number 4 is equivalent to which bar number in SI system? 30. Number 30. 34. Okay. Number 30. But it is more important to remember FPS system because everyone in Pakistan uses FPS. I mean these bars in US customary numbers. Okay. Now you need at the bottom 0.3975 inch square total reinforcement. Okay. And if you decide to use number 4 bar, then number of bars at bottom equal to what? The area you need 0.3975 divided by area of one bar, which is 0.196. So can you please quickly do the math? Can you put your laptop in the
What is it?
It's not showing that there are 3 bars now.
2.028.
What is the answer?
2.028. 028.
Okay, and use what? 3 number 4 bar. Okay, use 3 number 4 bars. And how about the edges? You can continue the same 3 number 4 bars, but make sure that you check this for A minimum, S minimum. If this value is less than AS minimum, then you have to provide at least AS minimum. Now that's your PRC course,
Yes.
right? Okay. Now, how about the top part? You can see that top part here is 0.44 and here it is 0.5. If they are close to each other, you can provide the same reinforcement here as well as here, right? 0.5 and 0.44, no big difference. Or if you are picky, you can have a different reinforcement here and have a different reinforcement here. But generally when the difference is small, such engineers provide same reinforcement. Yes, in the middle, there is no significant negative bending moment. So you can, for example, right here, how many bars you need? Can you quickly divide this with 0.196?
So
2.4
bars.
It's 2.6. No, it's
Same 3 bars.
it is 3 bars. It's again 3 number 4. Okay, so you provide 3 number 4 here and 3 number 4 here. In the middle, you don't need 3 number 4. So you can do what? You can curtail one of the bars and have 2 number 4s because you need something to hang the shear reinforcement. So use as a hanger bar. Okay, so instead of, you can have 3 number 4 here, but right here you can have 2 number 4. Okay, so it's something like this. So right here at the bottom you have what? 3 number 4, and at the top right here on the support you have 3 number 4, you have 3 number 4, and in the middle you can curtail the bar and you can have 2 number 4 here, right?
तो इस तरफ बना दो इसका जो
you can, I'm not going to sketch more, but you can just sketch it at the end. I just want to explain you that at the bottom you have 3 number 4, at the support you have 3 number 4, at the support you have 3 number 4, and in the middle you can have 2 number 4, and you know where you curtail. You remember where you curtail? Exactly at L by 3. Okay? This is about longitudinal reinforcement. The second is shear reinforcement. These curtailments are taught in PRC1 and PRC2. So, the job of the software finishes here. Okay? And beyond this point, it's your detailing, PRC knowledge. So, I will mostly curtail the things here and then you can carry forward. This is longitudinal reinforcement. You can also display the shear reinforcement. Now, this option was previously inactive. Now, this option is also active, which says display. No, that was active before as well. Now, from here, you can pick which reinforcement you want to show. This was longitudinal, and now I want to see shear reinforcement. I want to see shear reinforcement. Okay. Press OK, and you see shear reinforcement. Now, you only see 3 values, because in case of shear reinforcement, there is nothing like top and bottom reinforcement. It is just a shear reinforcement. Okay, the values you see here are AB over S. One thing, you tell me, where we have more shear, at the edges or at the center?
At the edges.
Okay. For any particular beam, for example, this beam, see the value is 0.009, 0.003, 0.006. So you have at the edge more reinforcement. 0.002, 0.001, 0.01, and this one is 0.013. Okay. So at the edge you provide different reinforcement, and at the center you provide minimum. Okay. But you have to look at the magnitude. For example, I am taking this value to tell you how to calculate the reinforcement. This is 0.013. Okay. This 0.013 is actually AB over S. Okay. You need to understand this thing that the value software shows for shear reinforcement is AB over S. What is S? That is the spacing of the reinforcement. What is AB? AB is the area of shear reinforcement. How does a shear reinforcement look like?
Yes.
This is shear reinforcement, right? How many legs it has? It has 2 legs. Okay. So you will count the area twice. It has 2 legs, 1 and 2. And say we use number 3 bar. Generally for beams we use number 3 bar for shear reinforcement. What is the area AS of number 3 bar? It is around 0.1 inch square. Area of number 3 bar is 0.1 inch square. Area of number 4 bar was what?
0.196.
0.196. Almost double. Okay. Now AB is actually this, but this is area of 1 bar, and our shear spirit has 2 legs. So the area which we are providing is twice of this. So right here we should plug 2 into 0.1 divided by S equals 0.013. Okay, there are 2 legs, that's why we have 2. 0.1 is this area, and you equate it with the area the software is telling. What do you get for S? Okay, S equals to 15.38. This is in inch. 15.38 inch. Okay, which means that the shear reinforcement should be number 3 at the rate of 15 inches center to center. This is your shear reinforcement. But you have to check it. Check for S maximum. You know, shear reinforcement has a limit. No, I think they call it S minimum. Not S maximum. S minimum.
ये सारा मैनुअल बनना है चेक करना है मैक्सिमम कितनी होगी?
Yes, it's D by 2 I think. Actually there are different values. Yes, at least you should have that.
300 millimeter.
Or at the most you have that spacing. Okay, if you, for example, your beam is 15 inches deep.
Yes.
Okay, and the D effective depth is say 13 inches. So what is D by 2? D by 2 is 6.5. So you can't go beyond D by 2.
Yes.
Right? There may be another limit as well, but generally it's in that range. So you have to check it for maximum spacing. Yes, you're right. S maximum. So if this spacing is more than what is allowed, then you have to provide the that value which is recommended by the code. Okay, so you can go to your PRC notes and check it out.
सर ये तो मैनुअल वर्क से चेक करेंगे एस मैक्सिमम.
Okay, in this last beam you see here written OS. OS means overstressed. Okay, and the color is also red. So what you have to do is, you have to increase the size of the beam. I think we used 12 inch by 18 inches. And yes, on a right click, you can see a lot of information. It shows that for decon 2 at location 172 inches, the beam fails in shear. Shear steel, it says overstress. Its designation number 45, I think it's in its library that if it is overstress, the error is number 45, something like that. But OS means overstress. Overstress means increase the dimension. So how would you increase the dimension? You have to unlock the section, unlock the model, go to define, okay, and define a new section which is bigger. Maybe this was 12 inch by 18 inches. Maybe you need 15 inch by 18 inches, or you can use 12 inches by 21 inches. I mean, whatever. Increase the size of the cross section and use that cross section here, and then you can expect that it is not overstressed. So we don't want red. Remember, we want greens, right? Make sure you have green. Okay. Similar work is there for the column. Let me display the longitudinal steel again for the column. Okay, let's pick any column. Oh, you see that by mistake we designed it as a beam, this corner column. You can make such mistakes. But anyhow, let's pick this column. This column says that, first thing, this is longitudinal reinforcement. Okay, it says 2.25. What is 2.25? This is area of steel, longitudinal steel in inches. Okay, so 2.25 AS is 2.25 inch square. If you are using number 6 bar, say use number 6 bar. What is the area of number 6 bar? AS 1B. 0.75 is the diameter of this bar. Okay, that's 6 by 8 inches. The area of number 6 bar is 0.44 inch square. Okay, so how many bars? Number of bars are equal to what? 2.25 over 0.44. What do you get? 5.1 bar. So that's actually 6. So you shall use 6 number 4 bar. Oh, sorry, number 6 bar. 6 number 6 bar. That's your longitudinal reinforcement. Okay. So in this way you can go from one column to the other and see what reinforcement you need. Do you remember the size of this column?
15 by 15.
15 by 15. Okay. What do you get when you multiply 15 with 15?
2.25.
Then you divide it by 100. What is the 1% of
2.25?
2.25.
Okay. 1% of the area of the column is 2.25, and that's exactly what our reinforcement is. What does it mean? This is minimum reinforcement for the column. Minimum reinforcement for column is 1%. Okay?
Yes, sir.
So this tells us that the size of our column only needs minimum reinforcement. In terms, it means that you can reduce the size of the column. Okay? You can reduce the size of the column and maybe you get more reinforcement, but the size, I mean not more than 2.25, but you can economize it. Okay? It's only 1%. Okay? You can actually see the percentage as well. That's the last thing. Maybe we can cover the design report later on. From the same menu you can check rebar percentage. You will see that it is 1%. Everywhere I think it's 1%.
1% of AG.
1% of the gross area of steel. Everywhere on all the elevation it is 1%. Yes. Area check कर रहे हैं.
ये हमें प्रोवाइड ए मिनिमम नहीं करता. जो हमारे पास सीट आ रही है वो ए मिनिमम के
ए मिनिमम से ज़्यादा ही होगी या ए मिनिमम होगी या उससे ज़्यादा होगी.
हमें चेक करना
आपको ए मिनिमम चेक करने की जरूरत नहीं है.
कॉलम से नहीं चेक करनी.
टीम में भी करके स्पेसिंग की जरूरत पड़ेगी. जॉब एरिया जॉब स्पेसिंग कैलकुलेट कर
एफ मैक्स.
Okay, let's quickly have attendance.
अटेंडेंस हो गई.
Okay, please pay attention. Yes, Mr. Yes, right here. Start it.